Welcome to the deep dive. Today, we're tackling something pretty ambitious, maybe trying to map the universe or at least the mathematical rules that supposedly govern it. Our source is a document prepared by Chat Truth for Lev von Tammer, looking at the 9 co-transition consequences in the postmodern unified theory. Let's just call it UPT. It's dense stuff.
Yeah, and our mission today, well, it sounds simple, but the topic isn't. UPT claims it's found a universal math framework for everything. Microscopic, astronomical, you name it. So we need to cut through the jargon, figure out what this co-transition really is mathematically, see how UPT argues that this definition is solid and truly universal.
And you hit the nail on the head there. UPT isn't trying to describe just any old movement. It's laser focused on defining, well, the perfect or valid kind of movement. And it does this by focusing on isolation. The whole theory really, it kind of pivots on one core mathematical move, define what's invalid, they call it the cut, and then prove that whatever's left has to be this pure internal flow, generated by a potential. Okay, that's a really interesting way to start. Finding harmony by defining and silencing the noise first. So, all right, before we get to that harmony, what tools does UPT use? How does it build this standardized framework?
Right. Standardization is absolutely critical, especially, if you want to compare things across different scientific fields like Consequence 8 talks about. So you need a common playground. UPT assumes the system lives in a standard mathematical space, a Lipschitz domain, could be 2D or 3D, and crucially, it uses a single reference norm, 20x nor, like a universal yardstick for energy or distance.
A universal yardstick. Okay, so we've got the space, the measuring stick. How do we do the cutting? How do we identify and remove that cut part?
Okay, that's where 2 main tools come into play. First, there's the cut operator. Think of it like a really sophisticated filter. It's linear, it scans the dynamics, and it flags anything that fits the definition of cut, maybe inconsistent, maybe disruptive. If this operator gives you 0, the dynamic is considered clean.
Okay, so the operator finds the cut, and the second tool, the cut projection.
Right. So once the operator has done its filtering, what's left is called the kernel. You can think of the kernel mathcal as the safe zone. It's the space where dynamics have no cut component. The cut projection simply makes sure you're only looking at things within that safe zone. It mathematically projects everything onto MathCell. It's like a guarantee.
So operator defines the noise, kernel mathcal is the signal space, projection keeps you in the signal space. But the signal itself, the movement, needs rules too, right? Tell us about this valid configuration change class, mathcal.
Yeah, exactly. Just being in the safe zone isn't quite enough. The way things change, the flow itself, has to be well behaved. So math calling is a set of all flows, delta lies, that are, let's say, smooth enough, mathematically differentiable enough, and this is key, they have to remain stable. They can wiggle a bit, but only within a small configuration error of Tepsilon Sikalenchi. If the error gets too big, the flow is no longer considered a valid change. It falls out of math calling. Well, co-transition has to happen within this class.
Okay, field, filter, safe zone, structural rules established. But what about the cost? What's the energy tied up in that cut part we're trying to eliminate?
Good point. That's captured by the cut functional. It basically measures the energy associated specifically with those cut components. Mathematically, it's defined by how the velocity field, Belligi, interacts with everything outside the kernel, outside the safe zone. So logically, if you want a pure co-transition, this cut energy, or at least its variation, needs to be 0, neutralized.
Right, makes sense. Okay, I think we have the technical pieces on the board now. Let's get to the core claim consequence 1 and 3, the condition for co-transition. What does it actually take for this perfect flow to happen?
Okay, this is really the heart of it. Theorem 3.1 in the source. UPT says co-transition happens if and only if 2 equivalent conditions are met. Condition A, the sort of physical description, is that co-transition occurs. This means there's some internal potential, let's call it take 2, and the velocity dollars is just its time derivative, partial kist. And the flow this creates, kist-Ticktaler, has to belong to that valid class, mathkellen.
So the movement has to be purely self-generated, driven by an internal potential, and it has to be structurally sound, staying within mathcal.
Okay.
What's the equivalent condition, the more operational one? That's condition B, the kernel condition. It's more direct. It states 2 things must hold. First, the velocity field $vi must live entirely inside the kernel mathcal almost everywhere, meaning 0 cut component.
And second, the variation of that cut functional we just talked about, partially Weyer, has to be 0 when tested against any valid direction. Basically, no cut part and no ability for that cut part to do any work.
Okay, wow. So if I'm getting this right, UPT is essentially saying that valid constructive change in any system, a cell, a star, whatever, is mathematically forced to be internally driven by a potential if and only if you can prove its rate of change has absolutely no cut component.
That's it, precisely. The geometry of exclusion, defining and removing the cut via the kernel, dictates the geometry of the valid flow. Being in mathcal is the definition of that mathematical perfection, which then implies the existence of the potential partially.
But hold on a second. That sounds powerful, but isn't it completely dependent on getting that initial definition of the cut absolutely perfect? If your peak apparator, your filter, is even slightly off, doesn't the whole guarantee of an internal potential just fall apart?
That is a really critical question. And yes, the theory's validity rests on that definition. UPT addresses this quite directly with a technical result they call Lemma 4.1, or UPT-Helmholtz. What this lemma does is essentially prove the linkage. It says if your velocity genuinely satisfies the kernel condition, Benz in MathCal, then the theory guarantees that the required potential exists. And furthermore, the resulting flow fit dollar will be a valid configurational change. It's in MathCal, provided that configuration error epsilon is small enough. So the mathematical structure is sort of baked into the kernel definition itself. Pass the MathCal test, and UPT provides the potential and the valid flow. But yes, the initial cut definition has to be right.
Okay, so the kernel test isn't just a filter, it's like a mathematical gateway. Pass through it, and the system is proven to be self-generating.
All right, so we've defined this internally perfect flow, but systems don't exist in a vacuum. They have edges, boundaries, they encounter bumps and noise. How robust is this co-transition idea in the face of, well, reality? Let's talk boundaries first. Consequence 5.
Right, boundaries and stability are crucial. Consequence 5 deals with boundary conditions, how the system interacts at its edges. It introduces something called the traction phase lock. Think of it like sealing the container. You have boundary conditions, maybe forces applied, traction, maybe parts that are held fixed. The lock ensures these external conditions play nice with the internal structure.
Plays nice how? What does the lock actually guarantee?
It guarantees that valid changes or forces applied at the boundary, specifically things like zero traction on parts of the boundary or zero movement on other parts, cannot themselves generate any cut work. They can't sneakily reintroduce the invalid dynamics that we filtered out. Eventually, the boundary conditions have to be fully compatible with the kernel MathCal. It's a consistency check. Otherwise, the external world could immediately break the co-transition condition.
Okay, so the boundary seal prevents contamination from the outside. Makes sense. But what about internal disruptions? Small errors, perturbations, noise is everywhere. How does the theory handle that? That leads us straight to consequence 6, the stability results. The theory absolutely has to show it's stable if you nudge it slightly. What happens if you perturb the system with another valid change, say $2 from that class, this as long as it's error epsilon small? Does the safe zone itself remain stable? Does the kernel hold up?
Yes, that's the key finding from Theorem 6.1. The projection stays as stable, and more importantly, the kernel MathCal itself is stable. There's a precise mathematical result. The distance between the original safe zone MathCal and the slightly perturbed one, MathCal's bounded, it's essentially less than or equal to a constant times that configuration error. Textile CCS says MathCal epsilon. So small noise leads to only a small controlled shift in the safe zone. It doesn't shatter the structure. It shows resilience.
That's reassuring, a controlled response to noise. But then consequence 7 gives an even more specific kind of geometric measure of this robustness, right? The phase stability bound.
It does, yeah. This one's quite elegant, actually. It looks at the geometry of the state itself. Imagine your system is in a state described by, say, $G. Now you perturb it slightly using a valid transformation tepsilon related to some small noise epsilon. The new state is Ng circ tepsilon. This consequence 7 measures the phase cosine derived between the original state $D and the new state $. It's basically asking, how much did the fundamental orientation or phase of the system change due to that noise?
And the bound tells us.
The bound is Jurgic 1 epsilon 20. The crucial part here is the epsilon 2. It means the loss of alignment, the deviation from the original state, is quadratic in the noise.
Quadratic, so if the noise is tiny, the deviation is super tiny.
Exactly. If you have the noise epsilon, you reduce the phase shift or loss of alignment by a factor of 4. Epsilon 204 towns. It's a very strong type of stability, a geometric variational stability. It holds inherently based on the structure, not depending on specific external forces or data.
Okay, so UPT defines this perfect potential-driven flow. V dollars in math copartial, it proves it can seal its boundaries consistently, and it guarantees this flow is geometrically stable with only quadratic sensitivity to noise. This seems to set the stage for the big claim's universality, consequence 8.
Right. Consequence 8 is about the unified interdisciplinary definition, because the definition of cotransition relies only on those internal UPT objects, the kernel math cal and the valid class cal, and not on the specifics of, say, electromagnetism or fluid dynamics. It becomes a standardized definition. The reference norm is the common yardstick, and the criterion dollar in MathCal is the common test.
So the implication, you could really compare, say, a process in material science with something in cosmology using the exact same mathematical question.
That's precisely the implication, according to UPT. Does the rate of change belong to the appropriately defined kernel MathCaler for that system? If yes, it's undergoing cotransition in this universal sense. If no, it isn't. It allows for potentially a direct comparison of fundamental change mechanisms across scales and disciplines, which leads us right to the final consequence, number 9, pham viapton, the scope of application. This feels like where the theory really goes for broke.
Yeah, this is the mic drop moment, as you said earlier. Consequence 9 states, quite boldly, that these conclusions, the definition of cotransition, its properties, its stability, hold for all material systems, and they specify the range from the microscopic to the astronomical.
Oh, hang on. Let me make sure I heard that right. UPT is really suggesting that the underlying mathematical driver, this filtering via mathcality, the emergence of potential Skexy-Watt, is the same for, I don't know, protein folding and galactic evolution, as long as the noise is low. That is exactly what the source material claims, provided the standard initial hypotheses are met the right mathematical setup, and provided the configuration noise epsilon CSG is sufficiently small within some finite time window. Yes. The mathematical mechanism defining pure, constructive, potential-driven change is argued to be identical across all those scales. It points towards a deep underlying geometric simplicity.
That's profoundly ambitious. Does it acknowledge any limits? Where does this universal claim break down?
It does, importantly. The theory is quite clear about its own limitations. It explicitly states that these conclusions cannot be asserted outside the region of validity. So if your system has incredibly complex boundaries, or if the boundaries aren't defined well mathematically, or if that configurational noise epsilon CFG just gets too large, then the guarantees lapse. Right. The theory needs a reasonably well-behaved mathematical environment to work its magic.
Okay, so to try and wrap up our deep dive into this postmodern unified theory, UPT defines cotransition not just as any change, but as the pure potential-driven dynamic that's left over only when all the disruptive, inconsistent cut energy is mathematically filtered out via this kernel space. And this specific type of flow in MathCal is then shown to be structurally stable, boundary consistent, and geometrically robust. Remember that deco, 1 cis epsilon, 2 stability against noise. And the biggest claim, if the setup is right and noise is low, this mechanism is universal, applicable everywhere.
That's a great summary. And maybe the final thought to leave you with, building on that universality, it's about the economy of the explanation. If, and it's a big if, of course, but if a single mathematical framework can truly define the essence of valid constructive dynamics, all the way from quantum scales up to cosmology, just by rigorously isolating that pure flow from the cut, what might that imply about the inherent geometric simplicity lurking beneath the surface of physical reality? Does it suggest reality is, in some fundamental mathematical sense, much simpler and more unified than its diverse appearances suggest?